Somewhere beneath a parking garage in Edmonton, Canada, 4 stories down, a network of concrete pipes stretches nearly a kilometer through solid earth. No compressor hums, no refrigerant cycles through copper coils, and yet, every summer, this buried system pulls warm air in from outside and hands it back 6 or 7 degrees cooler, ready to be pushed through an entire office tower. In Edmonton, Canada, the Epcor Tower is an office tower with a large earth tube system running 4 stories underground, with concrete pipes traveling 900 meters under a parking floor, estimated to cool the air by 6 to 7 degrees Celsius in summer and preheat it by 10 degrees in winter. No electricity bill spikes, no refrigerant leaks into the atmosphere, just dirt, air, and pipe, doing a job we now pay hundreds of dollars a month to accomplish with machines. So here's the real question worth sitting with. If a $50 length of concrete pipe, buried at the right depth, can cool a home all summer long, why did we walk away from it? Why did an idea that predates the Roman Empire get quietly buried, sometimes literally, under the rise of modern air conditioning? That's what we're going to dig into. Not metaphorically, literally. Before there was Freon, before there was a compressor cycle, before anyone had ever heard the hum of a window unit on a July afternoon, ancient engineers had already solved the cooling problem using nothing but the ground beneath their feet. In ancient Persia, builders constructed vast underground water channels called qanats, engineering marvels that carried water for miles beneath the desert floor to keep it from evaporating in the brutal heat above. These waterways and underground canals diverted water through a tunnel system that ran beneath buildings, with a vertical shaft tapping into the tunnel from the lowest room of the house, sometimes paired with a tower or chimney at the top. Air would be drawn up out of that cool underground tunnel, pulled through the rooms of the house and pushed out through the chimney at the top, leaving behind interior spaces that felt less like a desert home and more like a cellar. The result was a genuinely cool house with basement-style rooms that stayed almost chilly, similar to a root cellar. This wasn't a lucky accident. It was applied physics, discovered by people who never had the word thermodynamics, but understood exactly how it worked. The Romans took a version of this idea and built it directly into their architecture. Their hypocaust systems moved air beneath floors and through walls using a similar logic, that the earth itself could be recruited as a thermal battery, absorbing heat in summer and releasing it in winter. And this is where the science gets genuinely elegant, because it isn't about magic or mysticism. It comes down to one simple, measurable fact about soil. Go down about 1.5 meters to 2 meters below the surface, and the temperature of the ground barely moves throughout the year. At that depth, the temperature of the ground remains almost constant throughout the year, a figure known as the Earth's undisturbed temperature, which stays warmer than the surface in winter and cooler than the surface in summer, while the air above swings from freezing mornings to scorching afternoons. The ground a few feet down sits in a kind of thermal hibernation, holding steady around the same number season after season. That stability is the entire secret. If you can get air to travel through that layer of earth before it enters your home, the ground will do the temperature adjustment for you, for free, with 0 moving parts. This is technically called an earth-to-air heat exchanger, though most people who build them just call it an earth tube. It's essentially a series of metallic, plastic, or concrete pipes buried underground at a specific depth, through which fresh atmospheric air flows, getting warmed in winter before entering the building and cooled in summer. Picture a very long, very patient drinking straw buried in your backyard. Air enters one end from outside, travels slowly through several dozen feet of pipe surrounded by cool soil, and exits the other end noticeably cooler than it started. No electricity required beyond, at most, a small fan to keep the air moving. The system has picked up a small library of names over the decades, depending on where you find it. Ground-coupled heat exchangers, Canadian wells, Provençal wells, earth-warming tubes, earth-air heat exchangers, and even the ancient term hypocausts. But the underlying principle never changes. Dig deep enough, run air through it slowly enough, and the ground will quietly reset the temperature for you. The numbers involved aren't small, either. Builders working with earth tubes today talk about drops of 10 to 20 degrees Fahrenheit or more between the outside air and the air finally delivered into the living space. In one documented example, when it was 99 degrees and 99% humidity outside, the interior stayed a cool, dry 70 degrees. A 30-degree swing achieved with buried tubes alone. That's not a marginal improvement. That's the difference between a house that needs constant mechanical cooling and one that barely needs any at all. And the tubes don't just cool, they also dehumidify. As warm, moisture-laden air travels through the cooler pipe, water condenses out of it the same way it beads up on a cold glass of lemonade on a summer porch. The air cooling off inside the tube causes water to condense out, delivering cooler, drier air into the house. So it isn't just temperature control, it's a built-in dehumidifier, running entirely on the physics of buried pipe. If this sounds almost too good to be true for something built from concrete and dirt, you're not the first person to think so. Earth tubes had a real moment in the modern spotlight. It wasn't ancient history, it was the 1970s. During the 1970s and early 1980s, earth cooling tubes received a great deal of attention from architects, builders, and homeowners as an alternative or supplement to conventional air conditioning. This was the era of the OPEC oil embargo, of gas lines wrapping around city blocks, of a country suddenly forced to reckon with how much energy it was burning just to stay comfortable. Passive solar design, super insulated homes, and yes, buried cooling pipes all surged in popularity at once. For a brief window, it looked like the future of home climate control might not run through a utility meter at all. It might run straight into the ground. But here's where the story takes its first real turn, because the honest version of this history isn't a simple tale of a brilliant technology getting buried by corporate interests. It's messier than that. In practice, despite seeming like a good idea, earth cooling tubes turned out not to be very effective, both technically and economically, and only a few hundred systems were ever actually built, with limited data on how well they performed. That's a strange twist for a technology with literally thousands of years of precedent behind it. So what went wrong between the Persian Qanat and the American suburban backyard? The answer has less to do with the physics, which is sound, and everything to do with the details of execution, details that turned out to matter enormously. The first problem was water. Whenever warm, humid air moves through a pipe that's cooler than the air itself, condensation is inevitable. It's the same reason your bathroom mirror fogs up during a hot shower. In a well-designed system, that condensation is meant to drain harmlessly away. In a poorly designed one, it just sits there in the dark, inside a pipe, for months. Many systems built during the 1970s and 80s failed because improper installation allowed condensation to collect inside the tubes. And after a few years, that moisture developed mold or bacteria. Imagine breathing air that's been sitting in a damp, lightless pipe for weeks before it reaches your lungs. That's not a hypothetical fear. It's the exact failure mode that gave earth tubes their bad reputation, and it happened often enough to become the story people remembered, long after the well-built systems quietly kept working in the background, unnoticed. The second problem was even more serious, and it came from underground itself. Soil doesn't just hold stable, mild temperatures, depending on the region and the local geology. It can also hold radon, a naturally occurring radioactive gas produced by the slow decay of uranium in rock and soil. Radon is an inert, radioactive gas roughly 8 times denser than air, and it's the direct decay product of uranium. An earth tube, by its very design, is a pipe intentionally built to draw air out of the ground and pump it directly into your living room. If that ground happens to sit above a radon-rich deposit, a badly designed system becomes a highly efficient delivery mechanism for exactly the wrong thing. One homeowner who loved his earth tubes for years later had an air quality test reveal radon levels equivalent in cancer risk to smoking several packs of cigarettes a day. That's a genuinely frightening statistic, and it's the kind of anecdote that spreads fast, sticks hard, and makes an entire technology feel dangerous. Even though the underlying flaw wasn't the concept, it was a specific engineering oversight. And this is the part of the story that rarely gets told honestly. The actual research says the danger was never inherent to the idea itself. In general, the health and safety concerns around earth tubes were based on anecdotes and experiences involving improperly installed systems. And a well-designed earth tube system with adequate air exchange can actually help solve a radon problem rather than cause one. That's a remarkable detail buried in the middle of the controversy. The same physical principle that makes an earth tube pull outside air toward your home can, if engineered correctly with the right slope, sealing, and depth, be used to intercept and vent radon before it ever reaches the pipe supplying your living space. The technology wasn't the villain. Sloppy execution was. There's a third factor, and it's less dramatic, but arguably more decisive in earth tubes losing the popularity contest. Pure economics. Even when builders install a genuinely well-designed system, the energy savings tend to be so modest that it becomes difficult to justify the high upfront installation cost. Digging a trench 8 feet deep, running dozens of feet of properly sloped, properly sized pipe, adding gravel beds and drainage and insect barriers, that's not a $50 weekend project once you do it to code. A properly built system needs a wide trench at least 8 feet deep, several inches of gravel at the bottom, tubes at least 6 to 8 inches in diameter running around 80 feet, with a continuous slit to let condensation drain and a fabric sock to keep insects out. And that adds up to thousands of dollars. Compare that against a central air conditioner you can have installed in a single afternoon, backed by a manufacturer's warranty, serviced by any technician in town, and it becomes obvious why homeowners in the 1980s and beyond drifted toward the machine with the plug rather than the pipe in the yard. Then there's the invisible competitor that earth tubes were up against the entire time. Refrigerant-based air conditioning got cheaper, more reliable, and more mass-produced with every passing decade. As factories scaled up compressor manufacturing and electricity became the default utility running through every American home, the modern air conditioner simply became the path of least resistance. It didn't require understanding soil composition or worrying about slope and drainage engineering. You bought a unit, you plugged it in, and cold air arrived on command, regardless of how deep the water table sat beneath your yard. Earth tubes demanded patience, expertise, and site-specific engineering. Central air demanded a credit card. In a culture racing toward convenience, that trade-off wasn't close. But, and this is the discovery worth sitting with, the technology never actually died. It went quiet, it went underground, literally and figuratively, resurfacing not in suburban backyards, but in some of the most advanced high-performance buildings on the planet. The Environmental Science and Chemistry Building at the University of Toronto's Scarborough campus incorporates massive below-grade concrete earth tubes that feed fresh outside air into a basement ventilation unit, working in tandem with ground source heat pumps and 60 geothermal boreholes, each roughly 689 feet deep. This isn't a nostalgic throwback experiment. This is cutting-edge, passive house certified engineering, built by people with access to every modern climate technology available, who chose to include buried concrete pipe anyway because the physics still checks out. The University of Toronto is even applying earth tubes alongside passive house standards on infill student and faculty homes in downtown Toronto. So why does it work in these institutional projects when it stumbled in so many backyard attempts? The difference comes down to precisely the failures we already uncovered. Engineering discipline. Modern earth tube installations are designed with continuous slope for drainage, sealed to prevent radon intrusion, sized correctly for the airflow they are expected to handle, and built with materials chosen specifically to resist microbial growth. Well-meaning green builders have made elementary mistakes, such as using large-diameter concrete culvert pipe as an earth tube air inlet, when the details of design actually matter enormously to whether a system performs safely. The lesson embedded in decades of earth tube history isn't this technology doesn't work. It's this technology punishes shortcuts, which, if you think about it, is true of nearly every engineering discipline that interacts directly with the ground beneath a home. Plumbing, foundations, drainage. Earth tubes simply demand the same rigor, and for a long stretch of the 20th century that rigor wasn't consistently applied. There's also a quieter, more skeptical voice in this story worth including, because a fair account of any technology has to hold space for its critics. Some building science professionals remain openly unconvinced that earth tubes are worth the investment at all, even when done correctly. One prominent building science writer has stated plainly that he isn't a fan of earth tubes, arguing that while a well-installed system won't necessarily deliver damp or mold-infested air, the core issue is that the energy savings rarely justify the high cost of installation. That's an important counterweight to the more romantic version of this story. The ground beneath our feet really can cool air for free, but free doesn't include the cost of the trench, the pipe, the gravel bed, and the labor to install all of it correctly. In a world where a mini split heat pump can be mounted on a wall in a single day for a fraction of that cost, some engineers argue the math simply doesn't favor buried concrete anymore, no matter how elegant the underlying physics remains. And yet, the appeal hasn't disappeared. If anything, it's finding new life for a very different reason than it did in the 1970s. Back then, the motivation was the price of oil. Today, it's something closer to a reckoning with what our cooling systems actually cost the planet. Refrigerant-based air conditioning depends on chemical compounds that, when they leak, and they do leak, from aging seals, from careless disposal, from imperfect manufacturing, can trap heat in the atmosphere thousands of times more effectively than carbon dioxide. Earth tubes contain no refrigerant at all. There's nothing to leak, nothing to phase out under international climate agreements, nothing that requires mining rare compounds or running a compressor motor around the clock. It's just soil, air, and geometry, borrowed from an idea that Persian engineers understood 2,500 years before anyone had heard of hydrofluorocarbons. The picture that emerges then isn't a simple story of a brilliant ancient technology being crushed by greedy modern industry, and it isn't a simple story of a flawed idea rightly abandoned either. It's something more honest and more interesting than both. Earth tubes are real, functional, physically sound technology, capable of measurable, meaningful cooling, using nothing but a hole in the ground and a length of pipe. They faltered not because the science was wrong, but because the execution was frequently rushed, under-engineered, and undocumented. And because the alternative, mechanical air conditioning, became so cheap and so convenient that few people had the patience to get the details right. The concrete pipe was never really the problem. The shortcuts taken while burying it were, which brings us back to that tower in Edmonton, and to the university buildings quietly running buried concrete tubes beneath their foundations right now, in this moment, cooling the air with nothing but the patient, unchanging temperature of the earth below. The technology waited, It didn't disappear. It simply stopped being the default, sitting in the historical record next to solar chimneys and qanats and hippocausts, ready to be picked back up by anyone willing to dig deep enough and do the engineering properly. Somewhere, right now,